So this lecture and the next are going to be devoted to some very specific problem in graph theory, and that is the problem of finding or deciding whether there is a Hamilton cycle in a graph. So a Hamilton cycle is a cycle that uses all the vertices. Of a given graph. And today, we'll always be considering a graph called G. Its number of vertices, its order is going to be n, and we'll assume that that's at least 3, so that we'll have a chance of having a cycle. Right, a cycle through all the vertices of G is a Hamilton cycle in G. There's also a corresponding notion of a Hamilton path, a path that uses all the vertices. Okay. This is the same Hamilton that you probably know from linear algebra, maybe physics. So this one famous Irishman, 19th century Hamilton, and he sort of must have amused himself with this problem, whether in a given graph such a Hamilton cycle exists or not. There's an application of the notion that is undeniably useful, and that is the traveling salesman problem. So you have a graph and a salesman, that's one of those people in America that get in their car and they travel to lots of cities to visit customers, and apparently you can get from some cities to some other cities, but maybe not to all of the other cities directly. So you have a graph along whose edges this traveling salesman can travel, and these edges have costs. So think of it as distance or petrol used or gas used or something. And he or she wants to complete a cycle through all the clients, all the towns on this graph that costs as little as possible. So we're looking for a cycle through all the vertices of a graph whose sum of edge weights is minimum. That's the computational Hamilton cycle problem. And when you fix a cost that you don't want to exceed, like k, and you ask, is there a Hamilton cycle of total weight at most k, then that's a hard problem and one of the classical hard problems. Okay. So we're not concerned with algorithms here, so we'll just ask, does a given graph contain a Hamilton cycle or not? And the existence of a Hamilton cycle thereby is a graph invariant, which we can try to relate to other graph invariants. So let's think of what might force the existence of a Hamilton cycle in a graph. So you want some edges to be there, so it certainly won't harm if we assume that we have many edges. So can we assume sufficiently large, say, average degree to force a Hamilton cycle in any given graph? In our graph G on n vertices, what average degree would do that? Is there an average degree independent of n? No. Very simple example. If you have two complete graphs of roughly half the vertices overlapping, say, in just one vertex, then you can't have a cycle that contains all the vertices. You can't pass through this vertex more than once, right? And yet the degrees are about half n, right? So even a min degree let alone an average degree of any constant order, will force a Hamilton cycle on arbitrarily large graphs. But this is something like the worst that can happen. And if the min degree is bigger, then a Hamilton cycle exists, and that's Dirac's theorem. Let me just... It's 10.1.1. Okay. Dirac's theorem says that if the min degree is at least half n, then there's a Hamilton cycle in G. Okay. Right. How would we try to prove that? Well, let's look at a longest cycle. Well, let's look at a longest path. Let's look at the longest path in the graph. Now, if we can find, well, notice that the first and the last vertex have all their neighbors on this path, right? Otherwise, it wouldn't be a longest path. If we can find adjacent vertices on this path, such that the second is a neighbor of the starting vertex and the one before that is a neighbor of the last vertex, then we shall have a Hamilton cycle well, we'll have a cycle, and I claim it's a Hamilton cycle because if it wasn't, then we'd have a longer path. This graph is connected by the degree assumption, so let's write that into the assumptions. Anyway, so if this is not a Hamilton cycle, if it doesn't cover all the vertices, then there's another vertex adjacent to this, and then we'd have a longer path. We'd just hit that and then go round up to there. You've seen this argument before. Right, so if we can find such adjacent vertices, the right-hand one is the neighbor of the leftmost vertex, and the left-hand one is a neighbor of the rightmost vertex, then we're done. So let's prove that there are two such neighboring vertices on that path. Well, and for this, how do we encode this property that I want to target? By attaching it to, by rephrasing it as a property of one vertex. Let's phrase the existence of these two edges as a property of this vertex. What does it satisfy? This vertex is adjacent to XL, to the last vertex, and so that encodes the existence of this edge. This vertex is adjacent to XL. What does this vertex satisfy so that this edge exists? Well, the next vertex is adjacent to X1. So all we need is one vertex that has both these properties. It must be adjacent to XL, and its successor must be adjacent to X1. Okay. But these are properties that we're considering for at most n minus 1 vertices, right? We defined this only for the first L minus L vertices. No, L minus 1 vertices. Right? So those are not all the vertices of G, fewer than n minus 1 vertices. So think of these as pigeonholes. Right? And we want to fit some pigeons in these pigeonholes. And what pigeons do we want to fit in them? Well, the degree of this last vertex here is the number of vertices hit by an edge here. The degree of that vertex here is equal to the number of predecessors of neighbors of that vertex. Because every neighbor has a predecessor. Right? This is not a neighbor of itself. So every neighbor, and there are at least half n neighbors of x1, every neighbor has a predecessor. Every edge here and every edge there gives rise to a pigeon that wants to live in one of these holes. And how many pigeons are there? There are, well, there are n pigeons in n minus 1 holes. So one pigeonhole has 2 pigeons sitting in it, and that's our cycle of that type, and therefore a Hamilton cycle in the graph. Questions? Okay, that was Dirac's theorem. Now, what else can we say? Crude idea, in this example here, we needed the min degree assumption as big as that to not just get a cycle on all the vertices, but even to get any cycle that connects these two parts here. Right? So we might think, well, a one separator is not good for a Hamilton cycle. Maybe if we raise the connectivity a little bit, and rather than assuming a large average degree or even large min degree, how about assuming large connectivity? Right, that's a stronger assumption. Is there any absolute connectivity independent of n, exceeding which will ensure that we have a Hamilton cycle on n vertices? No. Here's a simple example. Let's say we have k vertices on the left and more than k vertices on the right, and we have a complete bipartite graph on k and L vertices here, then this graph cannot have a Hamilton cycle because any cycle must shuttle between left and right, and it can't visit right more often than it visits left. So this doesn't have a Hamilton cycle, but since it's complete bipartite, this is in fact k-connected. So which assumption, connectivity assumption, do we need to ensure we have a Hamilton cycle? Well, we need half n again. Right? So if L is just a little bit smaller than k, then we have connectivity just below half n and no Hamilton cycle. So, well, not better off than this. And then, of course, on the positive side, a min degree, assuming a min degree of at least half n is a weaker assumption than assuming connectivity of at least half n. So Dirac's theorem is not going to be replaced by this now, but this is a caveat. It shows that assuming large connectivity is not going to do wonders for us for the existence of a Hamilton cycle. Okay, next observation, this example here. Has many independent vertices. Right, alpha alpha of G is the independence number, is the maximum of the size of a set of vertices that are independent in G. Right, the largest number of independent vertices you can find in G, that's called alpha of G. There's also an omega of G, which is the largest size of a complete graph in G. Right? Alpha and omega are complementary here. Okay. So this example works because we're allowing alpha to be relatively large. How about forcing alpha to be small? New idea, clean slate. Does assuming that low alpha force a Hamilton cycle? Right? Lots of edges is something like we can't have large independent vertex sets. So it should help. But yes, but no. So if we have a kn minus 1, just one more vertex here, we don't have a Hamilton cycle, or even if it's connected, we don't have a Hamilton cycle. But we don't have large alpha, we have alpha 2. Right? No larger independent sets than sets of size 2. So making alpha small isn't good enough either. Making kappa big isn't good enough. Making alpha small isn't good enough. But the combination of the two is good enough. And that is 10, 1, 2. If alpha is at most kappa, then G has a Hamilton cycle. That has a pretty little proof. So this isn't just any assumption about alpha and kappa. It's the alpha we need to kill this example. Right? If we have this particular example in mind, if we're not assuming anything about kappa, then this gets in the way. But if you just want to kill this example, so we assume kappa connected, or say k connected, then this counterexample works if alpha is bigger than k, and the theorem is that if alpha is not bigger than k, if it's at most the connectivity, then the counterexample not only no longer works, but also there is no other counterexample. Okay, so let me try and prove that. Consider a longest cycle C. Okay. If that's not a Hamilton cycle, then there are some other vertices. Let D be a component of G minus C. Right, if such a component doesn't exist, then we're done, then we have found our Hamilton cycle. Okay. Now, use V to denote let me write it in longhand, neighbors of D on C. Right, so the vertices of C sending an edge to that component, let's call that V, and V plus the successors of the vertices in V in some orientation of that cycle. So if this is in V, little v, then its successor, say clockwise, is a little v plus. So every neighbor of D has a successor, which I call v plus if this is v. Right, we have two little v's now. Okay. Sort of theoretically, for the moment, this v plus could also be a neighbor of D, could also be a big V. But in fact, it can't. So let's observe two things. One is there are no V plus D edges. Right? So that's the same as saying that V plus is disjoint from V. Big V plus is disjoint from big V. Why? Well, if there was such an edge, from a little v plus to D, then we could find in D a path, because D is a component, a path from that neighbor to whatever sits at the end of this edge here of the little v that belongs to this v plus. Right? And then we could extend our cycle. We would find a longer cycle through here. Okay, so that would be a contradiction which proves this. And similarly, there are no v plus edges. And that's only a little more complicated. It's the same idea. So suppose there's an edge here. Right, then I go follow the cycle from this vertex to just before the other vertex. I mean, this is symmetrical. I could also do this from this vertex to just before the other one. Right, so there's no loss of generality here in me drawing it like this. So from this vertex, we go to the little v that belongs to the other v plus. Then we go into that component. Then in that component, we find a neighbor of the little v that belongs to the first v plus. Then go back to the cycle and round. And we've again used all the vertices that are on C, and we've used at least one more vertex. So these could be identical, but it's one more vertex at least. Okay, so we have proved those two things, but that's a contradiction. Why is that a contradiction? Because we have an independent set of how many vertices? We found order V plus 1 independent vertices. Right, all the vertices of V plus are independent. And we'll just pick one more in D, and that's also independent of all those in V plus by this here. So we have more than order V plus independent vertices, but the connectivity of G is at most order V, right? Because big V is the set of all the neighbors of D on C. And that separates D from the rest of C. Now you might ask, is there a rest of C? Yes, there is, because the blue vertices are not in V by this. Okay. That's the explanation for why we have a contradiction. Yeah. Questions? Okay. These were the two pretty theorems for the day. Now comes a stronger theorem. Right. That is 10(1,3). That's a theorem due to Asratian and Khachatrian. I asked Asratian how to pronounce his name, and in order to do this lecture properly and have it on record and so on. So he sent me a little audio clip with his name on it, but I can't do it very well. So it says Armen Asratian, something like that. And Khachatrian, I'm guessing. Right, 1990 or something. And it says that G has a Hamilton cycle if for every induced path U, V, W, so that's a path, U is adjacent to V, V is adjacent to W, but U and W are not adjacent. The following holds, and now comes something weird. Do I want this notation? Yeah. So the sum of the two degrees is at least the size of this set. Now, that clearly implies Dirac's theorem, the first one we had, this one here. Because if the min degrees are all at least half n, then this sum is at least n. And this is a subset of the entire vertex set. Right? So twice half n will be at least this, because this is at most n. The same proof that we had up here obviously also yields that if for every two non-adjacent vertices, these two here, the sum of their two degrees is at least n. We get a Hamilton cycle. I didn't mention that, but the same proof yields that, and that also follows from here, and maybe in some sense inspires this statement here. But it is a weird statement, and that is not uncharacteristic of the field of Hamilton cycles in graph theory. And the proof is even more typical, I'm afraid. But I want to give you a good impression of what graph theory can be, the attractive bits and the other bits as well. So let me try and indicate that proof. Yeah. Okay, so I'm giving you the proof in a way that is easiest to understand, but totally mysterious to see how one can possibly have hit this statement. So we might get back to that question later at the end of the proof to see how did they arrive at this assertion even. I mean, you don't say, okay, let's try and strengthen this, for example, like that. You don't. So they got to this assertion in some mysterious way, which maybe is a bit of a stroke of genius or requires that, I don't know, it certainly eludes me, but I'll indicate how they might have possibly found that statement right at the end of the proof. But now let's do it the other way around with hindsight, and let's just look at what the statement says. So we have this path, or for every induced path, U, V, and W, let's look at their neighbors. So U has some neighbors, and W has some neighbors. Maybe they have some common neighbors. Maybe not. And let's give that union of the two neighborhoods the color green. So that union features here. Right? Okay, now little v also has some neighbors. Maybe it has some neighbors on the left here, maybe some on the right here, maybe some in the intersection, and maybe some others. Right? So we'll be interested in those others, those that are not in green, in order to come to grips with this particular set here. We want to split that set into green and what remains. And what remains must come from this, but we don't want to count these twice. So let me draw that yellow. So yellow is the neighbors of little v that are not green. So without the neighbors of the set U, comma, W. And that is the green set here, neighbors of U and neighbors of W. Or same as this. Okay. Now, let's make this intersection blue. From this inequality, what does this inequality tell us? The sum of these degrees counts the vertices in blue twice. This here, the entire neighborhood of UVW is also green plus yellow. So this inequality means that this means that blue must exceed yellow. So let's look at what blue is. Blue are the number of vertices that are neighbors of U and of W. So they're counted twice in the degree sum. And those are just the neighbors of U and W altogether. So if we add to all the neighbors of U and W, those that are counted twice, then we get precisely to this sum of degrees. That sum of degrees counts the common neighbors of U and W twice, here and there. So this added to this here equals the sum of the two degrees, which by assumption is at least that big. Okay, so what is this set? This set is the neighbors of U and W and V. Those are the neighbors of U and W. So if you take those away, then what remains of this set is the neighbors of V that are not green. And those are the yellow ones by definition. So the neighbors of V that are not green. So we have this inequality as an observation of what our premise here yields. So we'll call this statement 1. And now, just see, yes. Well, in particular, the yellow set includes U and W. Right? U and W are not joint neighbors of U and W because U and W are not adjacent, so they're yellow. And in particular, the yellow set has size at least 2. So blue has size at least 2. And since blue has size at least 2, the whole thing has a cycle. Okay? U, V, W, and a vertex in blue and back. So there exists a cycle, which is a rather long-winded way of proving the existence of a cycle from this premise, but yeah, one has to do something. So let's consider a longest cycle. And let's prove that it's a Hamilton cycle. So same as before, except we're not considering another component now, but just one more vertex, little u, adjacent to the cycle, which must exist if this is not a Hamilton cycle, because we're assuming that the graph is connected. And then V is the set of neighbors of little u on C. So it has some neighbors. That's the set V, as earlier, the neighbors of the component D. And V plus, as earlier, are the successors. On C with an orientation of the little v's. So that's V plus. When we have a little v here, we have a little v plus associated with it. Okay. Now we have two statements again. The first is that v plus union the little u is independent. So same argument as earlier. If there was an edge from blue to blue, we'd find a longer cycle. And if there was an edge from little u to some blue, we'd also find a longer cycle even more easily. So that was as earlier. And we have a similar statement in that no two vertices in V plus union the little u have a common neighbor outside C. Right? Any common neighbor outside C, so that would be something like a subdivided edge violating this. Right? We'd get the same longer cycle rather than having a u v plus edge. We'll now have a subdivided u v plus edge, and similarly for two vertices in V plus, we can't have a joint neighbor, a common neighbor outside C. Okay, so let me call these two statements true. And in particular, these paths here, u, v, v plus, they're going to be induced, right? Because u and v plus are non-adjacent by this. So since they're induced, we can apply the premise to such little paths here, and we'll do that in just a moment. Okay. So let me see what this assumption here, this inequality here, means in our particular case where v plus is the little w. Right? This little w is now, we consider this path uv v plus, so our w here from the arbitrary path uvw that was induced is now going to be v plus. So let me just copy what we have over there. So for every little v, we have the number of joint neighbors, of common neighbors between u and w, is at least this here, yellow. That's the neighbors of little v, there's little v here, that are not neighbors of u or v plus. I'm just copying without thinking. Right. Now, oops. Let's look at these vertices in here. Any vertex that is a neighbor of u or this particular v plus here, any such thing is not in v plus. Okay, but that means that if we're taking away from the neighbors of little v something that is not in v plus, then intersecting with v plus is not going to harm us. So this set is certainly no bigger than that set. And in addition, we have the little u, which is a neighbor of v, but is not in this set. And not in this set either. So that's for the little u. Did you get that? So once more, the little u is a neighbor of v, but it's not in v plus, so it counts for this, but doesn't count here. And it's not taken away here. So what does this count here? This counts the neighbors of v plus that lie in this set. What neighbors of v plus are also neighbors of u? Well, nothing outside C. Right? The neighbors of v plus that are also neighbors of u must be on C. So the neighbors of little v plus that are also neighbors of u lie on C and are therefore in big V. So this here counts the v plus V edges. Yeah. And this here counts the V plus edges. And at this point, you can, it might trigger an instinct which is called double counting. So if we have a bipartite graph, in this particular case it'll be the graph with vertex classes V and W, any bipartite graph, so that has some edges, right? Notice that little v's send an edge to their v plus, but also possibly to some other v pluses. So this graph may have lots of edges. And this here counts for every little v the edges incident with that v. This counts for every little v plus the edges incident with this V plus. And if we sum over all of them, then both count the same set, namely the number of these edges. Right? V plus, that's these here, plus 1 is at most this. So minus 1, but when we sum over all little v, then we're counting every little v once here. So this is a contradiction that completes the proof. Yeah, so you can ask yourself, of course, as I would ask myself too, and have asked myself, but not particularly successfully, of how all these ideas somehow make a hodgepodge that gives that theorem in the first place, that theorem. And I think it's probably, I mean, this definitely comes at the start. This was all known stuff, right, from the previous argument up there that was long known. And then maybe what came next is this double counting to see that we have the V plus edges here and the V plus V edges here, and they count the same thing. And then we required for a contradiction, and the little u counts here. Right? And then in order to get a contradiction, we needed this inequality. And then one could search for conditions that might imply this inequality, and to get this inequality takes us to wanting this, to wanting 1, to wanting just blue is at least yellow. And then one can ask, okay, how do we ensure that blue is at least yellow in the particular case of little w being a V plus? To say, well, we can't really say what the V pluses are in a general statement, so let's just say for all induced paths of length 2. Because those paths that we're interested in, where we wanted, happen to have length 2. And then you're here for all induced paths of length 2. You require whatever makes inequality 1 true, and that is counting the degrees and looking which neighbors are counted twice. So that's all I can offer by way of explanation for how to find that theorem. There's certainly a stroke of genius in finding that. Also, if you look at their original paper, it's full of similar things. So there are lots and lots and lots of theorems that sort of play with conditions like that. That is just the one I found easiest to communicate, let me say it like that. But the paper is full of similar conditions, all technically strong in a sense. Well, not all of them, but I mean, this implies a host of strengthenings of Dirac's theorem that existed before. So it is a good theorem in the technical sense of implying lots of other things that were there before. It's also a very technical theorem. So whether finding that statement came out of some vision of what really makes Dirac's theorem and its strengthenings true, or whether it came out of playing around with the scenarios that were known and seeing what one could say, I don't know. It's certainly not something that I would have ever wanted to find. But it's typical for the whole area of Hamilton cycles in graphs. So all the arguments are very pedestrian and sort of looking here and there and seeing what happens if you change that vertex and if you move along here rather than along there and so on. So that's characteristic for the field, and therefore I thought it's a good thing to include in this course. But you don't have to learn the proof for the exam. Yeah, any questions?